We have spent a significant amount of our energy and of our time so far talking about how numbers are represented in the machine by the computer. We talked about 2's complement and all the details about the binary representations that are needed. You may be wondering, isn't this a programming class? Isn't this how the computer sees the numbers? Why would I, as a programmer, need to care about it? I can write numbers in the decimal system. And this is completely true. We don't need to know the 2's complement if we want to perform a simple operation like 5 minus 7. We can write decimals when we're writing our programs. But here is the trick. If we want to really understand the limitations of the machine, the limitations of what we can do, and how to avoid specific weird mistakes, corner cases, then we really need to understand how the computer represents numbers, so that we are not surprised by unhappy incidents. The kind of surprises that we want to be able to avoid are known as overflow and underflow. And it is important not only to avoid them, but also understand why they might occur. They are kind of going hand in hand. And they both of them have the root cause being the same. In overflow, the problem is that when we are adding two numbers, the result is too positive. Now, what does that really mean? Imagine that we only have 3 bits for the representation. Even imagine that we don't represent any negative numbers. So we're talking about unsigned interpretation of those binary numbers that result from 3 bits. What is the largest positive number we can represent in an unsigned representation with 3 bits? Think about it, and I will not reveal that to you right now. But think, for example, the following. Would you be able to represent the addition of 7 plus 7 in that system? What would the result be? The result would need to be 14. Can we represent the number 14 when we only have 3 bits? This is what we mean by too positive. Let's see a specific example, and here I will provide more answers. Suppose that we want to represent numbers, both positive and negative, with 8 bits, and we are using 2's complement. What is the largest positive number we can represent with 8 bits in 2's complement? It will be 2 to the power of 7, 8 minus 1, minus 1, so it will be 100. 128 is 2 to the power of 7. The greatest number will be 2 to the power of 7 minus 1, so 127. 127 is the largest positive value we can represent with 8 bits when we're using 2's complement, so when half of the range goes to represent negative numbers. And what happens if we make the addition 127 plus 1? What we want the addition to result to will be obviously 128. However, what will actually happen is that we will get a negative number. We will actually get the most negative number we can get, minus 128. The reason we get minus 128 can only be explained if you know the details of the 2's complement. How do we represent the largest positive number, 127? It will be a leading 0, and the rest of the bits, the other 7 bits, will all be 1. Now take this number, the first one, the most significant bit 0, all the others 1, and add 1 to that number. What will you end up with in binary arithmetic? You will end up with a number that has the leading bit, the most significant bit, being 1, and all of the rest of the bits being 0. But that is exactly the representation of the most negative number, the smallest negative number in the representation with 8 bits, the minus 128. This is why when you add 1 to 127, the result will be minus 128 and not the expected. This is an example of an overflow and an example of why it happens, why this particular result that we will see on our screen will be there, and why you shouldn't expect to get answers in such occasions. When we actually start programming, we will see specific examples in code. How about underflow? Underflow is the other side of the coin. It is a problem when the difference of two numbers is too negative. Again, in a system where we have 8 bits, 2's complement, what is the most negative number, the smallest number we can represent? We already said it will be minus 128. What happens when I try to represent an even more negative number, an even smaller number in the system? So I go and subtract 1 from minus 128. Then I will not get the result needed, the correct result. The result will actually be 127. And in order to understand that, write the two numbers in binary. Write minus 128 in binary. Write minus 1 in binary, 2's complement. Add them and see the binary result that you will get. It will be the positive number 127. What is critical to realize is that Java will not warn us about any of these operations if we try to do them. Java will quietly ignore overflow and underflow. It is completely up to us. It is the programmer's responsibility to know of these dangers and avoid them. We already mentioned dangers. What else could go wrong in our programming lives as far as the binary system is concerned? We might expect that if we multiply the decimal number 3 with the decimal number 0.3, we will get the decimal number 0.9. This is unfortunately not quite the case, and you can try it. We will try it in later examples as well. The result that you will get is something similar to what you see on your screen, so very close to 0.9, but not exactly 0.9. The reason for that lies to how real numbers are represented in the machine. We have already mentioned the binary system and how we represent integers. We haven't talked again about real numbers. This is something that we will do in a later video, but we will not go into as much detail as we have gone with the representation of integers. Finally, I would like to recommend a website on number systems that you might find useful to revise things or see more details.